Hello friends. By way of understanding the fundamentals of statistics, we've been looking into different distributions, and in the last session we looked into a function of one of these distributions. Now, if you could recollect, our discussion on the distribution began with the consideration of a single independent variable. In our case, we assumed this variable to be the lattice parameters of different alloys. So when we have a collection of the lattice parameters of different alloys, it allowed us to place these different alloys on a scale, and when we have numerous such alloys, we will be able to see the distribution of the population of these alloys on that scale. So this allowed us to translate the distribution of the population. So essentially what we have is a single independent variable. From this single independent variable, by using a scale, we were able to arrive at a population distribution. So from the population distribution, we were able to introduce a bin. So bin is nothing but a range of these lattice parameter that we have measured. So when your lattice parameter of your alloy, it falls into this range, we place it under the bin. So there is a possibility of more than one alloy occupying a specific bin. So what essentially we have done is, so this population, the distribution of the population, we have collected it in the forms of the bins, and each of these bins are range of lattice parameters. And now when you have a collection of alloys in a bin, we stacked it one over the other, and that led us to what we refer to as the histogram. And from the histogram, we were able to rather fit a curve. So when you fit a curve over the histogram, we are able to arrive at a distribution curve. So we have a single independent variable. It is possible for us to represent the single independent variable using a scale. So in the scale, it was the measurement of the lattice parameter. So it was in the order of angstroms. We measured, or we were able to place the different alloys based on its lattice parameter onto the scale, and that gave us a population distribution. And when we introduced bin, we were able to arrive at rather the histogram. So population distribution on a scale, then using a bin, we were able to represent this population distribution as a histogram. And now when we are able to fit a curve over this histogram, we were able to arrive at the distribution curve. Now we saw that there are three possible or commonly observed distribution curve. One is a normal distribution curve, the other is an exponential distribution curve, and the gamma distribution curve. Now as it is the distribution curve, when you look at it, it just gives a representation, a schematic representation of how your histogram looks like, and we were able to rather describe the distribution curve for the normal distributions using mean and variance. Now in the previous lecture, what we did was we replaced rather the population that gave us this distribution curve. So basis for all this, both histogram and the distribution curve, is the population distribution. Now we replaced this population distribution in our previous lecture with probability. Now when we have an histogram and we have a representation in the form of the histogram, it is possible for us to replace the population distribution with probability. That is, when you consider a specific bin and the population in that bin is n1, then when the overall population is capital N, this gives us the probability of an alloy assuming the lattice parameter of that bin. So this is the probability of an alloy assuming the lattice parameter of that bin N1. So for each and every bin, it is possible for us to estimate the corresponding probabilities, and therefore it is possible for us to translate the histogram and the corresponding distribution curve into a probability curve, and that is what we refer to as the probability density function. So initially we were rather bereft of or devoid of any y-axis, and now when we translate the population to that of the probability using the expression that is applicable to the histogram, and now what we have essentially been able to do is replace or introduce a y-axis, a function that is based on the x, and this function we refer to as the probability density function. So what this probability density function essentially helps us do is, this probability density function, it helps us calculate the probability of an alloy assuming a specific lattice parameter. So in this case, the variable x is the lattice parameter. So this probability density function, it allows us to calculate the probability of a newly developed alloy assuming a specific lattice parameter. Now the way we were able to do that is, it is possible for us to estimate the probability of an alloy assuming a specific lattice parameter is by considering the area under the curve with respect to that specific lattice parameter that we are interested in. So if this is the lattice parameter, say xi is the lattice parameter that we are interested in, then the area under this xi would give us the probability of a newly developed alloy assuming this lattice parameter. So this is possible because now we have represented the distribution using the probability as in the form of a function, and this function for the normal distribution curve is expressed as this. So it is a function of x, where x is the only independent variable, and that independent variable in our case is the lattice parameter, and this function, even though the independent variable governing the function is x, it is dependent on characteristic parameters like mu and sigma. The mu here is the mean, and the sigma is the standard deviation, and the sigma square is the variance. So sigma square is the variance, and when you consider the overall expression, it is of this form: 1 by sigma square root 2 pi exponential of minus x minus mu square by 2 sigma square. So when you consider the overall comprehensive expression of the probability density function of a normal distribution, it is of this form here, where this function is dependent on, it is characterized by two different parameters, that is mean and the standard deviation or variance. Now it is possible for us to have a distribution, a normal distribution, wherein it is centered at 0. So the shape of the normal distribution is rather governed by the mean and the variance. So mean, it dictates the position of the normal distribution, whereas the variance, it dictates the width of your normal distribution. So when the variance is high, when the standard deviation is high, and the value is high, you have a sharper curve, and or rather when it is low, you have a sharper curve. When it is high, the spread of the normal distribution will also be higher. Now supposing when we have a case where the normal distribution is rather centered at 0, like that mu is 0, and the standard deviation is equal to the variance, and it is equal to 1, then in that case, what essentially we can get rid of is, it's the dependency of or the influence of these parameters. So essentially in those cases we have the probability distribution function of this form here. So based on the way we represent the probability distribution function, we will be able, particularly in the case of normal distribution, and even also in the case of Gaussian and or rather gamma and exponential distribution, based on the way we express this function, we will be able to state if it is a standard distribution or it's just a generalized one. So in this case, the standard distribution will be of this form, wherein we assume that the distribution is rather centered at 0, and its corresponding mean and the standard deviation, the variation and the standard variance and the standard deviation is equal to 1. So in such cases, the special case of the normal distribution, where it is centered at the 0 and the variance is equal to 1, we refer to it as the standard normal deviation, or rather a standard normal distribution, and the probability density function of standard normal distribution will be of this form. We can write it from this expression here. When you substitute the corresponding value, it will be 1 by root 2 pi exponential of minus x square by 2. So we have a generalized expression for the probability density function, that is PDF. This is the PDF for the Gaussian function, and the second one is the PDF for standard Gaussian distribution or standard normal distribution. The first one is the PDF for a normal distribution, the second one is the PDF for the standard normal distribution. Now towards the end of the last lecture, we saw that it is possible for us to convert any normal distribution to the standard normal distribution. So any normal distribution we can convert into to standard normal distribution, provided we are able to appropriately change or standardize this particular variable here. So if I'm able to standardize this variable and translate it into z, it is possible for me to express any normal distribution as the standard normal distribution. So supposing if I have an expression for x in this form wherein the mu is a non-zero entity and the sigma is not equal to 1, then it is possible for me to write this expression as this PDF in terms of z, translate this variable to z in such a way that these conditions, that is mu for z is 0, so mu prime, let us assume this to be mu prime, that is when the variable is not x but now is z, and for the new variable z, mu prime is 0 and sigma prime is equal to sigma square prime, which will be equal to 1. So whereas in the previous variable the mu was a non-trivial entity, it has a specific value, and the sigma was not equal to 1, it is possible for us to rather express or replace the variable with a suitable variable wherein the mu, now the new mu of this new, for this new variable, for this new curve is equal to 0, and the sigma or the variance of the new function is equal to 1. Now such process is what we refer to as the standardization. So this we refer to as the standardization, because ultimately we are translating any normal distribution to a standard distribution. Now this z can be expressed as the way we arrive at, or the way we translate the variable x to z, and again the characteristic feature of z is the mu corresponding to that variable z, the function. When we replace or write the function instead of p of x and translate it into p of z, the mu for this case is 0 and the sigma is equal to 1, and it is possible for us to do that when we use or when we estimate the z from the x using the mu and sigma. So this mu and sigma are associated with the original function or the original variable x, and by combining these characteristic parameter with x in this manner, it is possible for us to arrive at a new PDF, a new probability distribution function, which is rather standardized. So what essentially we are doing is we are translating p of x, which is dependent on mu and sigma, using this expression here into p of z, where mu is 0 and sigma is equal to 1. So what essentially we have now seen is we have introduced a distribution, or rather a density function, a probability density function for the normal distribution, and we saw that there are specific parameters that describes the nature of this function, and it is possible for us to calculate, to estimate the probability associated with a specific variable using this function. And now, even though it is possible for us to have a wide range of normal distribution, meaning it is possible for us to have a normal distribution that is centered at any point on the scale, and the variance could be anything, it is possible for us to translate any of these normal distribution to a corresponding standard normal distribution by appropriate change in the variable. And in order to bring about the appropriate change in the variable, we have to use this expression here. So we are changing the variable from x to z, and this process is referred to as the standardization. Now when we want to rather consider the probability of an alloy assuming a specific lattice parameter, so that is what we have been looking into. So we are considering a normal distribution of this sort, and we want to consider the probability of an alloy assuming a specific lattice parameter. So for instance, I want an estimate of an alloy assuming the specific lattice parameter here, say for instance x1. Now in order to estimate the probability of an alloy assuming or a specific lattice parameter x1, so x here represents the lattice parameter, and what we have is the PDF along the y-axis. Now when we want to estimate the probability of a given alloy assuming the lattice parameter x1, what I need to consider is I need to consider a specific width. I need to provide a specific width for me to estimate the area under that curve, because when I give a specific value, the area under the curve will become rather 0, and I will not be able to estimate the probability. So a feature that we need to understand while we are estimating the probabilities from the PDFs is that when I want to rather estimate the probability of my alloy assuming a specific lattice parameter, I need to create a certain degree of tolerance and certain degree of width to the specific lattice parameter that I am interested in. So if x1 is the lattice parameter then that I am interested in, then I have to provide a certain degree of width. Only then I will be able to estimate the area under the curve. If I'm just exclusively focused on x1, then I won't be able to estimate the area under the curve, because x1 then will provide just a straight line to me. So in order to do that, we introduce two neighboring point. So I need to provide a width. So I introduce x plus h1 and x minus h1, and x minus h1 I call it as a, and x plus h1 I call it as b. So this point are a and b, and the a is x1 minus h, and b is x1 plus h. Now it is possible for me to calculate the area under this curve, and this will give me the probability of the alloy, rather the probability of the alloy assuming this particular lattice parameter, the lattice parameter that is close to x1. Okay, when I'm attempting to estimate the probability of lattice parameter of an alloy assuming a specific lattice parameter, even though I refer to it as a specific lattice parameter, owing to the characteristic approach that we are adopting to estimate this probability, I need to provide a width. And this width is rather, it is what brings about a measurable and estimatable area under this curve. And now when I'm able to do that, when I'm able to provide that width, then the probability of an alloy assuming the lattice parameter of x1, again, which is dependent on, now we don't really know if this curve is a standard normal distribution or is it's a generalized one. So it is dependent on, again, that this is a function that is dependent on mu and sigma. Then the probability of an alloy assuming a lattice parameter of x1 will be the integration between a to b, the PDF p of x, mu comma sigma dot dx. So what essentially we have is this expression for the normal distribution is known to us. We have looked at it we have looked into it in our previous slides. And now we are integrating this particular function within a specific range, and this specific range gives a width to our desired lattice parameter. And once you have a discernible width, it is possible for us to calculate the area under the curve. And that area under the curve is essentially what will give us the probability of the newly developed alloy assuming that particular lattice parameter. Now it is possible also for us to rather estimate what is the probability of the alloy assuming a lattice parameter that is not just x1, but rather it ranges from 0 to x1. So what essentially we have is, supposing our lattice parameter is L, so we are considering a lattice parameter, this L is rather greater than 0, but it should be less than or equal to x1. So let me repeat, what essentially in our previous case, in this expression here, we are considering or we are estimating the probability of a newly developed alloy assuming the value of x1. So for that we are considering we are creating rather a specific width, and we are measuring the area under the curve for that specific width. Now our goal is to estimate what is the probability of the newly developed alloy to assume the value from 0 to x1. So it should range from 0 to x1. So the least to the one that I desire. So it is something, the least is here and the one that I desire is here. So all the area under this overall curve here. So essentially what we want to estimate is, we want to estimate the probability of an alloy assuming a lattice parameter that is greater than 0, but that is less than or equal to my desired value that I previously calculated. So the desired probability that I previously calculated is x1. So it should be the lattice parameter of the newly developed alloy L should be less than or equal to x1, but it should be greater than 0. So it is possible for us to calculate that, and what essentially we need to consider is, we need to consider the same function and the appropriate range for it. So we need to consider the same function but the appropriate range for it. So here the range starts from 0 to b. So this function, let us call it as a fancy c of x1. Again, it is dependent on mu1 sigma, which is it will be equal to 0 to b, the probability distribution function x, which is dependent on mu1 sigma dx. Now this function, it is referred to as the cumulative density function. So rather this is what we estimate. This is what we refer to as the cumulative density function. What essentially it gives us the cumulative probability of the newly developed alloy, assuming this particular range of lattice parameter. So earlier we were interested in a specific lattice parameter. Now we are interested in the wide range of lattice parameter. So we have a desired lattice parameter and we want to estimate the cumulative probability. So it is possible, if you can imagine, it is possible for us to estimate the probability of an alloy assuming this particular range of lattice parameter. It is possible for us to assume or estimate the alloy assuming this particular range of lattice parameter, and it is possible for also us to estimate this particular the probability of an alloy assuming this lattice parameter. It is also possible for us to estimate. So all we need to do is consider the appropriate ranges here. It is also possible for us to estimate the probability of a newly developed alloy assuming this range of lattice parameter. So all we need to do is consider the area under the curve. So what essentially the cumulative density function gives us is, it gives us the cumulative probability, summing up of all the probabilities that precedes or that is less than our desired lattice parameter. So x1 is our desired lattice parameter, and what we need to estimate is what is the probability of the newly developed alloy assuming a lattice parameter that is equal to our desired value or it is less than our desired value. So the condition is being stated here. So the probability we are estimating for the newly developed alloy, it can either be, there are two conditions we are imposing. One, it needs to be equal to or less than our desired value, and its value should be non-zero. It should have a specific value. So that is what we refer to as the cumulative, that is what we refer to by this condition here. And using the appropriate bounds, we will be able to estimate the cumulative distribution functions from that of the probability distribution function, and we will be able to estimate the cumulative probability from rather the cumulative or from the probability distribution function. So this essentially again is the probability distribution function, and using the appropriate bounds, we will be able to express the cumulative distribution function. The reason why we call synonymously use the cumulative distribution function and the cumulative probability is because if I substitute the generalized expression that we have for the probability distribution function of the normal distribution here, and then when I solve it and leave the expression as it is, then what we would end up having is a cumulative density function. Let me repeat, we have a specific expression, the probability PDF for the normal distribution, and if I substitute the PDF for the normal distribution and solve for this and leave it as it is, just as an expression alone, we would end up having the cumulative density function. We would end up having CDF. Now if I solve for this function here and I end up with a specific value and I end up with a specific or an estimate, then that would give me the cumulative probability. So therefore that's the reason why I've been using the cumulative density function and the cumulative probability synonymously. The reason is because depending on how we are handling this particular expression here, where we are stopping at this particular expression, we can treat it as a cumulative density function or a cumulative probability. But the fundamental feature of it remains the same. What it essentially does is, in addition, so while the PDF allows us to calculate the probability of an alloy assuming a specific lattice parameter, the cumulative density function, it allows us to estimate the probability of an alloy assuming a lattice parameter and any lattice parameter below it, a specific lattice parameter and any lattice parameter below it. So that is essentially what CDF allows us to do. And again, how we handle this function, if we arrive at a specific value, that gives us the cumulative probability. If we leave it as a function, we end up having a CDF. Of course, we have already seen what the nature of this function is, and it is possible for us to use to handle this function appropriately. So now when you consider the trend of the cumulative distribution function, it will be of this form here. So this here what we have is a PDF, that is a probability distribution function for a normal distribution, and this here is what we have is a cumulative distribution function for a normal distribution. And as you can see, the cumulative distribution function gradually increases, and as we go towards the maximum value of the lattice parameter, the maximum value of the variable, it reaches the value of 1. So essentially what we are doing is we are considering, so when you consider each and every point of this particular curve, for instance if you are considering this point here, say x1, what essentially this point here means is the area under the curve from the least to x1. So I have considered a point x1, the same point I am considering here. So this area under this entire curve, that is x1 and below, is being captured here. The same way, if I keep on increasing, if I keep on moving my x1, correspondingly the value of how the area would increase is what is given by this red line here, and that is what we refer to as the cumulative distribution function. So the cumulative distribution, the trend of the cumulative distribution function for a normal distribution is like this. And this cumulative, so it's a monotonically increasing one, and these often we can express this in the form of a tan inverse curve. So when you keep on moving, when your x1, the point that you are interested in, is when it keeps on increasing, the way the corresponding area would increase is of this form here. And when you move closer to the maximum value assumed by the n or assumed by the variable, then the value of the area will become close to 1. So this is the trend associated with the cumulative distribution function for the normal distribution. So essentially what we have seen is, we have seen from the normal distribution, we have arrived at a probability distribution or density function for the normal distribution, and from the probability density function for the normal distribution, now we have cumulative density function for the normal distribution. Now let us move on to the other two distributions that we have considered while we consider the different forms of distribution, and one form of the distribution is what we refer to as the exponential distribution. Now in the same way, when you consider the way of translating the exponential distribution to exponential function, so what essentially we are doing is, in case of the distribution, we have represented it in the form of an histogram, and from the histogram we were able to arrive at a distribution curve. And when we replace the population with probability, we end up with a function, and this function is what we refer to as the probability density function. And again, this probability density function, again we need to understand the background, the physical significance of it. We are considering the lattice parameter. So all this is possible. The physical sense to all that we are discussing is that we are considering the lattice parameter assumed by the different alloys. Now this, if you consider the function that represents the way the probabilities of different parameters in case of an exponential distribution, this function, this PDF for the exponential function can be expressed as, so again we will use the same notation. Now this is p of x, so this is for the exponential function. The function will be of this form here, that is lambda beta exponential of minus lambda x minus mu and beta. So this is rather the PDF, the probability density function of an exponential function. Now again we need to understand that this is dependent on the independent, or this function is dependent on the variable x. So x here is the variable, and that is the principal independent variable that governs this particular function. However, the nature of this overall function is dictated by lambda, one parameter, beta another parameter, and mu another parameter. So in case of the first key difference that we need to understand when we compare the exponential function with that of the normal function, or the exponential distribution with that of the, when you compare the exponential distribution with that of the normal distribution and compare the PDFs of the exponential distribution from that of the normal distribution, is that in case of the normal distribution, the characteristic PDF was described by the independent variable and also at two other parameters, that is we saw it was mean and the variance. in the case of exponential function, the PDF for the exponential distribution, what we essentially have is we have three distinct parameters in addition to the independent variable that governs the nature of the PDF. Now, the mu here is referred to as the location parameter. So what essentially the mu governs is the location parameter. So when you consider the exponential distribution, what essentially the exponential distribution, when you want to rather qualitatively describe the exponential distribution, what it indicates is that, particularly again to discuss the nature of the exponential distribution, let us again consider the lattice parameter example that we have been considering. So what the exponential distribution indicates is when you consider the n number of alloys that we have, most of these alloys assume a lattice parameter that is in the range of the least lattice parameter, that is in the range of the least value. So you have n different alloys and you measure the lattice parameters of these n different alloys, and when you arrange them in the rather increasing order, most of these alloys assume a value that is around the least, and when you increase the value of the lattice parameter, the amount of alloys assuming that increased lattice parameter keeps on decreasing. So that is rather the qualitative description of the exponential distribution. So exponential distribution means that the value assumed, the materials or alloys assuming the least lattice parameter is higher, and as the lattice parameter increases, the population of the alloys assuming that particular lattice parameter, the increased lattice parameter, progressively decreases, and that is what we refer to as the exponential, and that is what is rather captured by the exponential distribution. And the PDF, so when you replace this population, the increased population at the least lattice parameter or the least value, and the progressive decrease in the population as we increase the lattice parameter values, when you replace this population distribution with the corresponding probability, you end up with the PDF of this form here. And now this mu, it dictates the location of the maximum population. It dictates rather the location of the least value. So in our case, the least value will be close to 0.1 angstroms. So that is what this mu rather it captures. This mu captures where the maximum population or the maximum probability is being positioned, where the exponential curve starts. And the beta here it is referred to as the scale parameter. So mu, it refers to as the starting, it rather captures the starting point of the exponential distribution, and beta, it often captures the scale of the exponential distribution, and lambda is referred to as the rate parameter. So we have mu, the location parameter, and lambda, the rate parameter, and beta, the scale parameter. Now often what we essentially have as the condition that we generally often face is the x, the variable, the mu is often greater than or equal to that of the variable. So this is the condition that needs to be satisfied for the exponential function, and beta is always positive. So the exponential function, it adheres to this particular condition here, that is the location. Again, what it essentially means is it has this particular exponential function has to start from a specific point, and that is dictated by the location parameter, and that location parameter, when you are considering the context of the exponential PDF, these two conditions needs to be satisfied, that is beta it should be greater than 0, and the mu, the location parameter, should be either less than or equal to that of or the corresponding x variable that we have considered. So when you have a range of lattice parameter and the mu corresponding to that of the lattice parameter, the range of lattice parameters that we have should either be rather the one of these lattice parameter value, or it should be less than these lattice parameter values that we have considered. So when you consider a specific lattice parameter, the mu of the corresponding exponential PDF should be, so if for instance I'm considering a specific lattice parameter of x1, the corresponding mu should be either equal to that is the portion of the exponential function, it should either be equal to that particular, so here the mu should be either equal to this x1 or it should be less than this x1. So if this is the mu that I'm considering, it should either be equal to x1 or it should be less than that. And so that is what is rather captured by, so that is the condition that needs to be fulfilled for the PDF of the exponential function, and beta, it needs to be a positive value. Now often what we have is this mu, the position function, is rather equal to 0, because often when you have x when you have a lattice parameter, when you treat x as the lattice parameter, which is often positive, which cannot be negative because we are talking in terms of the lattice parameters, and therefore the mu is possible for us to have a mu that is equal to 0, because again x in our case is a lattice parameter, so it cannot be a negative value. So therefore the condition that needs to be fulfilled is rather the mu should be greater than or equal to that of the mu should rather be less than or equal to that of the lattice parameter. So this mu 0 fulfills that specific condition, and beta 1 is another condition that, or another specific condition that satisfies this original condition, a specific case that satisfies this original condition. So these two are the original condition for the PDF of the exponential distribution, and these two conditions can be satisfied by these special cases here. That is, particularly when you are considering a quantity like lattice parameter, which cannot have a negative value. So the values of the lattice parameters are a part of the positive real numbers. So in that case, these conditions can be satisfied when mu is 0 and beta is 1. So this simplifies our PDF for the exponential function. So now the PDF for the exponential function is just dependent on one parameter, that is lambda, and it is so the whole expression can be represented as lambda exponential minus lambda x. So, or a simplistic way of writing it would be lambda e power minus lambda x. So this essentially is the PDF for the exponential function. Now this PDF, the simplified PDF, we have arrived at by, for a special case when the mu is equal to 0 and the beta is equal to 1, and this special case satisfies the original condition. So we have a characteristic description for the exponential function, and this characteristic description involves three different parameters: a scaling parameter, a rate parameter, and a location parameter. So the location parameter, it helps us understand from where the exponential curve starts, and the scaling parameter, again the name indicates it scales, and the rate, it gives us the shape to the exponential curves. So depending on the rate, you will see the trend associated with the exponential curve. The rate, again as the name indicates, it governs the rate of a curve or the slope of the curve. So that is governed by delta, and beta, it scales the different variables, and mu, it dictates the location of the PDF of the exponential function. Now for the PDF of the exponential function, there is a specific condition that needs to be satisfied, and when you consider a special case of the specific condition, so you have a specific condition that needs to be satisfied, and we are considering a condition that satisfies this original condition, a case which satisfies the original condition, then we end up an expression of this sort here. Now this is the expression for the PDF of the exponential function, and again now, instead of being dependent on three or influenced by three different parameters, this PDF is dependent on one parameter, that is the rate parameter, and again as the name indicates, the rate parameter rather dictates the slope of this curve. Now one other way this particular expression is written as, one other way of writing this expression is of this form: lambda e to the power minus lambda by x u of x. So the same PDF for the exponential function can be also represented in this manner, where u of x is 0 when x is less than 0, and 1 when x is greater than or equal to 0. So the PDF of the exponential function can be expressed in these two ways, that is p of x lambda is lambda e power minus lambda x, or the other way. This is one way of writing, and this is the other way of writing, where the u of x, this u of x which is augmented in the other way of writing, is that as a conditional function, this u of x is equal to 1 when x is greater than or equal to 0, and when it is less than 0, when the x value is negative, this whole entire function turns to 0. Now here again, the whole reason we have to introduce this function, or we are considering this particular function, this conditional function here, is because we are talking in terms of, we are considering the lattice parameter, and this lattice parameter, the x associated with it, it has a starting point, meaning this x, it belongs to, or it fulfills this condition here. So what essentially we have is the exponential function, the starting point of the exponential function in this case is either 0 or it is close to 0, and it has no relevance whatsoever in the negative region of your quadrant. So it has this entire expression, the entire exponential function doesn't have any significance when the value of the variable is negative. The value of the variable that we are considering, the principal variable x, when it is negative, this function is just null. So this function is not operational when the value of the variable is negative. The function is operational only when the value of the variable is positive and when it is positive. So when you write the probability distribution function for the exponential distribution in this form, it is implicitly assumed that in this form, when you write it in this form, the first form, it is implicitly assumed that this condition is being satisfied. It is implicitly assumed that x is of significance, and x, it belongs to the real numbers, the positive real numbers. When this condition is not explicitly stated, the generalized way of presenting the PDF for the exponential function is with using the u of x here, where the u of x is 0 when x is less than 0 and u of x is 1 when the x is greater than or equal to 0. So when x is rather positive, then essentially what we end up having is the same, we will be end up recovering the same expression here. When the x is negative, again in the generalized case, the entire exponential, the PDF becomes rather insignificant when the x assumes a negative value. So there is a qualitative description associated with the exponential distribution, and we have now seen the PDF of the exponential distribution. Originally it is rather described by 3 different parameters, and now we have reduced these 3 different parameters rather using this condition here. So we have reduced these 3 different parameters, 1, 2 and 3. So all these 3 different parameters, we have replaced it, or we have reduced it to 1, and this we were able to do by considering a specific case. So we considered a specific case of the generalized condition, and we were able to reduce the 3 different parameters to 1. Now all the subsequent expressions are associated with this specific case, with this special case here. So all these subsequent expressions, that is both these two ways of writing they pertain to the same PDF for the exponential function. So this PDF is associated with the specific case, and from this specific case we arrive at this condition here. So when you say that mu is 0, what essentially you are talking about is, or what essentially we are focusing on, is the independent variable that can assume the value in the positive quadrant of the real numbers. So in that case, the PDF is expressed as, it can be expressed in 2 different ways, that is lambda e power minus lambda x. Now again, when this condition is, so both these stem from the same condition, and when this condition is explicitly stated earlier, we can write the PDF in this manner. If it is not explicitly stated, it can also be written in this manner, wherein you include u of x, and u of x assumes in a relation of this form, and essentially what this means is also this special case from the generalized case, from the generalized condition is assumed. So this special case, or this case, is what renders the translation from a complicated PDF to a simplistic one, and because of this translation, it is possible for us to write this expression in 2 different ways. Write this expression using just the rate parameter, and this condition, if not explicitly stated, can be included by using another function u of x. So what now we have seen is, we have seen the PDF for the exponential function. So once we have the PDF for the exponential function, so again when we state explicitly the mu is 0 and beta is 1, the PDF for the exponential case, now which is dependent on the rate parameter alone, lambda, it can be expressed as lambda exponential minus lambda x. I hope I have captured it right. Now in this case, when I want to estimate the probability of an alloy assuming the lattice parameter, so we have a collection of alloys, and its lattice parameters are rather exponentially distributed, and now I want to find out the probability of a newly developed alloy assuming a value of x1. This is the x1. I want to find out the probability of the newly developed alloy assuming a value of x1. Similar to the previous case, we need to introduce 2 bounds, a and b. So a would be x1 minus h to give us a width, and b would be x1 plus h. So this would create a bound. So the probability of a newly developed alloy assuming a lattice parameter of x1 would be within the bounds a to b p of x lambda dx. So this will help me understand, this will help me capture estimate the probability of a newly developed alloy assuming a desired lattice parameter of x1. Now this gives me an estimate of the probability. Now it is possible for us to also estimate the cumulative distribution or the cumulative probability, meaning from the least or the probability of an alloy assuming a value from the least to the desired value. So meaning the probability of an alloy assuming a value. So this is the lattice parameter that we are interested in. So this should be, the lattice parameter should be equal to or less than x1, and it should be greater than the least, that is 0. So the probability of the newly developed alloy assuming a value that should be equal to or less than the desired value of x1. So equal to or less than the desired value of x1, and again, since we are talking in terms of the lattice parameter, so all the possible lattice parameters, they rather stem from 0. So because we cannot have a negative, so it's 0 to this particular value. Again, these are rather subjective to the condition that we are working on. Here the L that we are considering is the lattice parameter, so the lattice parameter should always be positive. So therefore, when I say that we are considering a range of lattice parameters, particularly in this case we are considering a range which is less than the desired value, less than or equal to desired value, and the other bound, the other end of the range comes from the nature of the quantity, that is the lattice parameter. It cannot be 0, so it's from 0 to x1. So in that case, what essentially we can do is, so the x1, the upper bound for x1 is rather b. So in that case, using appropriate bounds, I'll be able to calculate this probability. This probability is nothing but the cumulative probability. Again, instead of just considering one specific lattice parameter values, now I am considering all the values that are below the specific lattice parameter value, ranging from 0. So when I use the appropriate bounds, I'll be able to estimate this cumulative lattice or the cumulative probability. Now, like I said, it is possible for us to solve for the way we handle it. It is possible for us to estimate the cumulative probability or write it as a function. So the way we handle it, it is possible for us to arrive at the cumulative probability or write it as a function. So when we substitute this expression here and integrate it, what we end up having is 1 minus e power lambda x. So essentially this would be the CDF of the exponential distribution. So what we have done is, we have now treated the PDF in such a way that it ends up, and using appropriate bounds, it ends up giving us another function, and this function is nothing but the CDF of, or the cumulative density function of the exponential distribution. Again, it is possible for us to estimate a specific value, to arrive at a specific value, that will be cumulative probability, and now we have arrived at a cumulative density function by rather integrating this particular expression, and now essentially it is a form of function, and this function is the cumulative density function. So what we have seen is, we have looked into the cumulative, so we have looked into the PDF and CDF of the normal distribution. We have looked into the PDF and CDF of the exponential distribution function. Now when you consider the trend of the exponential, the CDF of the exponential distribution, so the expression we have seen in the previous slide, when you consider the area under the curve, the progressive increase in the area under the curve, it is of this form here. The trend is of this form here. So this is the trend that captures the progressive increase in the area under the exponential function. So as the bound, as the desired lattice parameter increases, the corresponding area under the curve also increases. The CDF, the way the CDF varies as the variable varies, is of this form here. Now with this we will wind the lecture up, and we will look into the other gamma function in the subsequent lecture. Goodbye.